You've learned some different functions in the past. One of the first functions you were introduced to were linear functions. They're the y equals mx plus b type functions, or here's an example, y equals 3x minus 4. You've also spent quite a bit of time working with quadratic functions, such as y equals 5x squared minus 7x plus 2. But in this video, we're going to take a look at what's called rational functions. And they have this form. Y is equal to some function in the numerator divided by some function in x in the denominator. So an example would be something like this. 2x minus 5 divided by x plus 3. This would be a rational function. And what makes it a rational function is there's a variable in the denominator. That makes it a rational function. So these ones here, the linear and the quadratics, they have variables, of course, in them, but there's no variable in the denominator. So rational functions have an x in the denominator. So the simplest rational function would be this one right here, y equals 1 over x. That's a very simple rational function. What we're going to do is we are going to take a look at this one here. Let's start by graphing the function y equals 4 divided by x. So I've got a graph here, and I'm going to start by just making a table of values. Often when we're doing a table of values, we'll start with 0 for x because it's an easy number usually to put into our function. But note what happens here. If we put 0 in for x, I got 4 divided by 0. Well, we know we can't divide by 0. So in a rational function, the denominator cannot equal 0. So in this case, if I try to put 0 in for x, 4 divided by 0 is not going to work. So this is going to be not defined. We will not have a y value when x is 0. Let's try some others right here. Let's try an x value of 1. Well, 4 divided by 1 is going to give us a point. So when x is 1, y is 1, 2, 3, 4. So there's 1 point on the graph. I'll try 2. 4 divided by 2 is 2. So when x is 2, y is 2. I could try 3, but 4 divided by 3 doesn't work very nice. So my next x value I'm going to pick is 4. 4 divided by 4 is 1. So when x is 4, y would be 1. And let's try another value here. Let's try 8. 4 eighths, 4 divided by 8 is 1/2. So when x is 8, 1, 2, 3, 4, 5, 6, 7, 8, y is 1/2. I think you can see what's happening here. We're going to get a nice smooth curve. If I continue to make x very big, so if I continue to go like 8, 10, 20, 30, 4 divided by 30, and 4 divided by 100, these y values are going to get small, but they'll stay positive. So if I had a number like 1,000 here, 4 divided by 1,000 is not a very big number. It's still a small but positive number because a positive divided by a positive is a positive. So these numbers are, if we connect these dots, if I continue to make x big, these numbers are going to get smaller and smaller and smaller, but still stay positive. If I try a number like, let's get these points on here. If I try a number like 1/2 or 0.5, 4 divided by 1/2 or 4 divided by 1/2 is 8. So when x is 1/2, I've got 1, 2, 3, 4, 5, 6, 7, 8. I'm way up here. So what happens when x gets really, really, really small is my y value, 4 divided by a really small number, gets very big, very large. And you can see if I get my calculator out, if I go 4 divided by, and I pick a really, really small number like 0.00001, I'm going to get a massive positive y value. So when x is a really, really small number, 4 divided by a very small number gives me a very large number. So this is why I put a little arrow on here, because this is going to go up and up and up. So this is one part of the rational function. What we haven't looked at yet is the negative x values. let's pick these same values here, -1, -2, -4, and -8. And I think we can see if I go 4 divided by -1, I'm going to be -4. 4 divided by -2 is going to be -2. 4 divided by -4, -1. And 4 divided by -8, -1/2. So I'm going to generate the same y values. It's just that now a positive divided by a negative is giving me negative values. So -1 is -1, 2, 3, 4. -2 is -2. -1, 2, 3, 4 is -1. And -5, 6, 7, 8 is -1/2. So I connect these with a nice smooth curve. And now what happens if I make x small, so close to 0, but negative? So let's make it a very small negative number. Well, we know that a positive divided by a negative is going to be a negative. And 4 divided by a very small number is going to give me a very large number. Again, you can see this on the calculator. If I go 4 divided by negative, but a very, 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 very small number, I'm going to get a massive number that's negative. So what that means is, when I make x a small negative number, this is going to go down, 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 like so. And if I make x a very large negative number, like a billion, 4 divided by a billion is very small. But of course we're doing a positive divided by a negative. So I get -4 times 10 to the -8. This is in scientific notation, which means the decimal has to go to the left 8 places. So that's a very, very small number. But it is negative, because a positive divided by a negative is a negative. So as my x value gets large negative, like -20, 30, 40, these y values are staying negative but getting very close to 0. So this would be the sketch of the graph y equals 4 divided by x. Now that we've done that, let's look at some of its properties. So let's start by talking about the domain. So the domain is, again, all the possible x values, or how far left and right this graph goes. So it goes to the right forever and takes care of all x values that are positive and takes care of all x values that are negative. The only x value I don't have a point on here is at 0. So the domain would be all real numbers, xer, all real numbers, but x is not 0. Not equal to 0. And same thing for the range. It goes down forever, it goes up forever, but the one y value that I don't have a point on is at 0. So for the range, y is all real numbers, but y is not 0. If we're talking about an x-intercept, which we often do with a function, in this case we don't have one, because the graph never crosses or touches the x-axis. So no x-intercept. And same thing when you look at the y-axis, we have no y-intercept. Now when we have rational functions, there'll always be some non-permissible values because we can never divide by 0. So the non-permissible value here is x cannot equal 0. Because we can see on here, we have a place where we have no y value for this x value. X cannot equal 0. And our asymptotes, now just to review what an asymptote is again here, there are 2 of them on this graph. One of them is, let's make them red. One of them is right here. And an asymptote is a line that the graph gets closer and closer to, but never touches. So this graph here, as we get really close to 0, as x gets closer and closer to 0, the y value is getting closer and closer to infinity. It's going up and up and up. Same thing here. As x gets close and close to 0 from the left, or from the negative direction, so if we say as x approaches 0 from the left, the y value is going down to negative infinity. And in another course that you take in calculus, we'll talk about these as being limits. So we can say the limit as x approaches 0 from the right is positive infinity, the graph is going up, and as we approach 0 from the left, the graph is going down. So what we have here is a vertical asymptote, and the equation of this line is x equals 0. Every place on this asymptote right here, x is equal to 0. So that's our vertical asymptote. Our horizontal asymptote is this one right here. And what I can say here is as x approaches infinity, if I go farther and farther and farther to the right here, the y values are approaching 0. And if I go to the left forever, so as x approaches negative infinity, if I go to the left forever, here again, the y values are getting closer and closer to 0. So in this one, I get y is equal to 0 as well for a horizontal asymptote. So those are the properties of rational functions. And you can see that rational functions are going to have these often different parts of curves. The graph will be split up. We'll have two different places here. In this example, anyway, we've got a couple of different curves. We get kind of a disjointed function. Let's look at some other rational functions. Let's say we're given this function here, y equals 3x minus 1 divided by x plus 2. Let's say we're asked to sketch the graph of it and come up with its properties. So I'll make a little graph here. I'm going to go to my graphing calculator. I'm going to enter this function here. So I got 3x minus 1. Make sure you put brackets around your numerator because we have more than one thing that we're going to divide here. Oops, minus 1. So 3x minus 1, close bracket, divided by another bracket, x plus 2, close bracket. Now we'll draw it. Now, I remember from the last example we did, we should see two parts here. So I might need to play with my window a bit here. I'm going to enlarge this here to standard, so minus 10, 10, minus 10, 10. And okay, now I'm seeing the two parts here. So looking at this sketch here, it's looking like we're going to have an asymptote here at minus 2. So let's draw an asymptote here at minus 2. And this curve is going to look something like this, just as a rough sketch. Oops. Let's look at that graph again. So we have a horizontal asymptote here. It's looking like it's going to be 3 on this graph. Let's get that one in. Whoop, get back to the right color here. And the other one is up here. So here's a sketch using the graphing calculator of this function. So let's do its domain and let's do its range. Now just notice we had this asymptote here of minus 2. How can we get that? It's easy to find, roots, which is our x-intercept. So x-intercept is at about 1/3. So we can get that from the graphing calculator. Whoops. Maximum and minimums, well, these functions go down forever and up forever, so no max and min. We can get the y-intercept. So when x is 0, y is negative 1/2. But how do we find out where these asymptotes occur? So one way of finding where some of these asymptotes are is go to the table function hit enter. Make sure you've got your function in there. Same one we've got here, 3x minus 1x plus 2. Then we can go to set, and I have it starting from minus 5 and going to 5. And then when I hit table, this is generating the y values for each of the x values. And you can see that when x is minus 2, it ends up with error, which means we've got a value that doesn't exist there. In other words, we have an asymptote. And then here's our other values for each of the different x values. So that's one way where you can find the vertical asymptote at vertical asymptote is at x equals minus 2. The other way you can find this is you can take a look at your denominator, which is x plus 2, and we know that that cannot equal 0. Can't divide by 0. And of course, if I bring the 2 to the other side, we get x cannot equal negative 2. So this would be our non-permissible value. And these asymptotes are so important. So the non-permissible value is at x equals 2. X cannot equal 2. Because once you know these asymptotes, we got the non-permissibles, we got what the asymptote is, we know that the domain is all real numbers, but not negative 2. Whoops, negative 2. Non-permissible is x equals negative 2. It's a little bit trickier to find out what the horizontal asymptote is. But if you think about it, the horizontal asymptote is what the y value is going to approach as x gets really, really, really big. So one way you could always find the horizontal asymptote is you could go to your calculator in the run mode, the regular mode here, and just put a massive number in for x. So go 3 times, I'm going to put in 1,000,000. What have I got there? One more 0. So there's 3 times 1,000,000 minus 1. There's the numerator, divided by, bracket, 1,000,000 plus 2. And let's see what we get. We get 2.9999993. So when I put a huge value in for x, the y value is getting obviously very, very, very close to 3. So my horizontal asymptote, if you can't see this from your graph, must be y equals 3. Because this graph is getting closer and closer and closer to 3. So the horizontal asymptote is the answer you would get for the function if you could make x infinity or really, really, really large. And so our range would be y is all real numbers, but y is not equal to 3. We'll look at one more example. Let's do this one here. Y equals 5x divided by x. And let's get domain, range, x-intercept, y-intercept, and so on. So let's pop the graph in here. So I've got it entered here already, 5x divided by x squared minus 4. And so now we get one that has sort of 3 parts to it. So we've got one, zooms along here, comes down. Looks like from my graph I can tell that there's an asymptote at negative 2 and another one at positive 2. So I'm going to put those vertical asymptotes in here. And that makes sense because if I take x squared minus 4 and set that equal to 0 and square root both sides, I do get x is equal to plus or minus 2. So we'll have asymptotes there. So our non-permissible values, we've already figured that out. The non-permissible values are x equals plus or minus 2. Let's go back and look at that graph. So it's just a sketch. I'm going to draw this little curve through here using my asymptotes as my guide. And I've got another part that comes down here. and appears to get closer and closer to the x-axis, and same one on this side. So there's a sketch of what the graph looks like. So domain, x is all real numbers, but not plus or minus 2. The x-intercept is 0. Let's just confirm that. So g-solve root, yep, 0. So x and y-intercept are 0. The vertical asymptote, we've confirmed that they are x equals plus or minus 2, this line and this line. The horizontal asymptote, it's pretty clear from the calculator that it's getting closer and closer to 0 as we go to the right and from the left, but we could just double check that by, again, putting a really large number in for x. So 5 times, I'll use 1,000,000 again, divided by bracket 1,000,000 squared minus 4. And yes, remember this isn't 5, it's 5 times 10 to the minus 6. That's what the answer is, which really means 0, 0, 0, 0, 0, 5, right? 1, 2, 3, 4, 5, 6 places. So yeah, this is getting closer and closer and closer to 0. And if I did the same thing, but stuck a negative sign in here, and of course on this one, I'm going to be squaring it, so it doesn't really matter if it's positive or negative, because squaring it's going to make it positive. Yeah, I get the same thing, except it's negative 0.000. So basically 0 as well. So the horizontal asymptote is this one here, y equals 0. So the range would be y is all real numbers, but y cannot be 0. Now, we've got to be a bit careful with that. So I was just checking here. I was getting carried away just by focusing on these ones here. Remember, we actually do have a y value of 0 when we look at this part right here. So this part of the function here actually does have a y value of 0. So we still have the asymptote at y equals 0, yes, because this part of the function gets closer and closer and closer to 0. But even though it never hit 0 here, and it never hit 0 here, this part of the function does hit 0. So you have to take into consideration the whole piece, not just these outside parts. So we have a horizontal asymptote of y equals 0, but our range of this function is y is all real numbers, because this part of the function, which goes down forever and up forever, is a continuous function. So just be a little bit careful when you start to get 3 parts of the function. You want to make sure that you're taking all of them into consideration when you're doing your properties.